In today's explainer, we're taking a deep dive into some seriously high-stakes engineering behind a critical electric vehicle hazard, the motor resolver offset error. This is literally the ultimate engineering butterfly effect. We're going to look at how an incredibly microscopic physical slip deep inside an EV motor can cascade into a massive, catastrophic electrical failure that threatens the entire control system. But more importantly, we're going to break down the highly sophisticated, multi-layered defense mechanisms that engineers designed to stop it dead in its tracks. Here is our roadmap for this explainer. First, we'll unpack the root cause analysis. Second, the software and hardware code diagnostics. Then we'll contrast the preventative design measures in DFMEA with manufacturing controls in PFMEA. And finally, we'll see how the whole system is stress-tested in DVP&R production validation. Let's just jump right in. Section 1, Fault Root Cause Analysis, the microscopic physical shift. Okay, let's dive into this. To really understand how we defend against this failure, we first have to understand the microscopic physical origins of the problem, because everything starts with the tiniest of physical movements. Imagine a totally microscopic deviation. We're talking just a 1-degree mechanical slippage or runout. Over time, under severe mechanical vibration, thermal cycling stress, or maybe just because a fastening screw slightly loosens, the resolver rotor can experience parallel eccentricity or an axial tilt. Now, why does this matter? Well, this tiny 1-degree physical slip alters the crucial relative zero point between the motor's rotor and stator. The controller is suddenly reading a zero point that honestly doesn't match the true magnetic pole position of the motor anymore. And here is where that tiny little slip snowballs into a massive problem. We immediately zoom out to the macro electrical impact, which is known as the pole pair multiplication effect. Because of how electrical angles are calculated relative to mechanical angles, that error gets multiplied by the number of pole pairs. So let's say you have a standard 20-pole motor, right? That has 10 pole pairs. That tiny 1-degree mechanical slip instantly blows up into a severe 10-degree electrical error. This causes dangerous cross-coupling between the direct and quadrature currents. The result? The motor loses up to 1.52% of its torque output, and it starts generating a massive amount of dangerous, unexpected heat. And this perfectly illustrates the 4 primary root causes of this ASIL D critical system failure. We have the mechanical slippage triggering the whole thing, the pole pair multiplication magnifying it, potential commutation data loss, usually from messy factory software flashes or service errors. And finally, thermal saliency, where extreme high-temperature loads cause deep magnetic saturation and physical distortion. Any single one of these can trigger a total collapse of the motor's position logic. Section 2, Software and Hardware Code Diagnostics, the race against time. So how does the vehicle actually know this is happening? This is quite literally a thrilling millisecond by millisecond race against the clock for the vehicle's control system to catch and neutralize the error before the hardware just burns out. Your very first line of defense happens before you even hit the accelerator. It's called ROL, or Resolver Offset Learning. During the vehicle's power-up initialization phase, while the motor is just sitting there stationary, the system actively injects a specific high-frequency signal into the stator windings. By analyzing those faint feedback currents, the software precisely calculates the current mechanical offset and automatically compensates for any accumulated assembly tolerances. It's basically the system zeroing itself out every single time it wakes up. But what if that slip happens while you're cruising at highway speeds? This is where the fault-tolerant time interval, or FTTI, comes in. The system has exactly 60 milliseconds to save itself. Step 1, the software detects an offset by spotting abnormal D-axis parasitic power consumption. Step 2, within just 5 milliseconds, it completely drops the physical resolver data and seamlessly switches to a software-estimated sensorless limpo mode, capping the torque at 30% just to get you to safety. But if that high-speed sensorless transition fails, Step 3 kicks in. The hardware takes over and executes a stepwise active short-circuit clamp, forcing the DC bus voltage safely under 720 volts. This is the ultimate failsafe to prevent a catastrophic electrical overstress burnout. Sections 3 and 4, DFMEA versus PFMEA, Design versus Manufacturing Defense. Relying on diagnostics is great, sure, but preventing the slip from ever happening in the first place, that's even better. Think of this as the Swiss cheese safety model. We're stacking different layers of defense, so if a hazard slips through one hole, it's caught by the very next layer. Now, what's really interesting about this slide is how we contrast the 2 main engineering disciplines protecting the system. Over on the left, we have DFMEA, the design side. This uses physical geometry and advanced algorithms to make the error theoretically impossible. And on the right, PFMEA, the manufacturing side, which uses high-tech surveillance on the assembly line to guarantee absolute perfection in the physical build. Looking a bit closer at the design side redundancies, engineers don't just rely on friction to hold the resolver in place. They use dedicated physical keyways and geometric step locks. It's a poka-yoke design that mathematically prevents slip. In the software, a high-resolution 2D inductance lookup table continuously decouples magnetic saturation distortions. But the most impressive part? They embed independent, redundant search coils deep inside the motor. These coils don't carry high drive currents, meaning even if the physical resolver entirely breaks loose, these coils provide a perfectly clean back electromotive force, or voltage reference. It lets the system instantly correct its angle data within that tiny 5-millisecond window. Over on the manufacturing side, the absolute obsession is tolerances. A critical metric you need to know here is TIR, or total indicator reading. This is a measurement of dynamic runout, or basically the wobble on the rotating surface of the assembly. To completely eliminate the physical pathways for that microscopic slip we talked about earlier, the manufacturing process strictly constrains this TIR to less than or equal to 0.05 millimeters. Achieving that 0.05 millimeter perfection requires some serious high-tech detective work on the factory floor. They run a gauntlet of automated checks. Step 1 is a 100% laser scan measuring the dynamic TIR on every single unit. Step 2 uses optical character recognition to verify that the bolts have the exact right phosphate coating, ensuring perfect friction before a 2-stage closed-loop torque angle fastening. Finally, Step 3 is a hard system lock in the manufacturing execution system. During the end-of-line test, if the motor fails to automatically calculate its offset or upload that data to the cloud, the system outright refuses to print a passing barcode. It completely eradicates factory escapes. Section 5. DVP&R Production Validation, Stress Testing the Defenses. So we've got a brilliant design and a flawless manufacturing process. But before this goes into mass production, we have to try and break it. This is where engineers put the entire defense system through extreme physical and simulated torture tests. Let's walk through this comprehensive validation matrix. First up, extreme mechanical fatigue. We're talking baking the motor at 150 degrees Celsius, spinning it at a blinding 18,000 RPM, and slamming it with 100 maximum torque impacts. The acceptance criteria? Absolutely 0 degrees of mechanical slip. Next, they use hardware-in-the-loop test benches to actively inject a sudden 10-degree slip while running at 12,000 RPM. This proves the software can actually catch it in under 60 milliseconds and clamp the voltage safely below 720 volts. Finally, the MES escape test. They intentionally inject 100 corrupted factory units into the system just to prove the factory software catches and physically isolates 100% of them. This whole journey really highlights the sheer depth of EV engineering. The resolver offset error is a microscopic threat, literally just a tiny physical wobble, but it has the potential to trigger a massive ASIL D system failure. But as we've seen, it is entirely neutralized by a macroscopic multi-layered defense architecture. We're talking physical geometry, dynamic algorithms, millimeter-perfect manufacturing, and absolutely brutal validation testing. Every single hole in the safety net is patched. Which leaves us looking toward the future. Right now, we can use advanced Python simulation tools to map dynamic tolerance windows across different pole care configurations before a physical prototype is even built. So the question I want to leave you with is this. As EV motors push toward higher speeds and even greater pole counts, how will dynamic computational modeling continue to push the boundaries of algorithm calibration and safety for the next generation of electric mobility? Thanks for joining me for this explainer, and keep questioning how the microscopic shapes the macroscopic in the technology all around us.